Hey, AP Chem. Welcome back to Chapter 5. We're going to talk through the rest of the chapter. This is Part 7 of Chapter 5. So we just finished talking about the kinetic molecular theory, and the kinetic molecular theory has 5 different postulates that explain what we are assuming is true about gases. And because these things are true, or we assume them to be true, it allows all of our equations and models in the gas chapter to function. It explains the why behind how they function. So we talked about how we can use kinetic molecular theory to understand the concept of pressure, to understand the concept of temperature. We're going to talk about how we can use the kinetic molecular theory to understand how these variables are related to one another. But before we do that, let's pause for just a second and talk about this idea of root mean squared speed. We took a look at this graph last class and how we can kind of draw certain information about it, like what the root mean squared speed for a warmer sample of gas is and what a colder sample of gas is. So I want to talk about this concept of root mean squared speed. What this is an average. It's the average speed of a molecule in a body of gas. So if we look at the graph above, look at the warmer sample. So what this does is it talks about the energy that is contained in each of the molecules in a certain body of gases. So in this graph, you can assume that under this curve is filled with molecules. So there's a molecule here, and that molecule has a specific energy. But not only is there one molecule here, there's a bunch of molecules here, right? And all of those molecules have that warmer speed, and we can actually fill out this whole curve under this curve, assuming that there's all of these kinds of different molecules in this sample of gas. And the thing that makes them different from one another is just that they are containing different amounts of energy. Okay, so for simplicity's sake, let's assume all of these gas molecules are helium, right? So it's just one atom of helium. It has 2 protons, it has 2 neutrons, it has 2 electrons, okay? And this is a molecule of helium. So if this whole body of gas contains helium, each of these helium atoms that I've represented by a red dot, they all contain a different amount of energy, right? They're all moving at a different speed. But if we add all their speeds up, okay, so, let's say right along this like peak in the curve, how many do we have? 1, 2, 3, 4, 5, 6, 7. So there's 7 molecules that have an energy of, let's say, 10. Then there's 6 molecules that have an energy of 9, and then there's 5 molecules that have an energy of 8, and so on and so forth. And if we add all these up and we divide it by the total number of molecules that we have, we would get an average speed, an average amount of energy that each of these molecules contain. And remember, the energy, if we're talking about kinetic energy, we're talking about motion, right? And motion can be described by speed. So what we would calculate if we did it that way would be an average speed. So this is one way to calculate an average, but as you go higher into math, and especially something like statistics or the math behind like science data and analysis, which is a whole bunch of statistics, what we find is there's not just one way to calculate an average. And actually in chemistry, we've already talked about 2 different ways to calculate an average. We can calculate like a straight arithmetic average, which would be this. We can also calculate a weighted average. And remember, weighted averages are used to describe like isotope mass. And so what we would do with a weighted average is we would take the percent abundance of a molecule of an isotope, and we would multiply it by the mass of that isotope. And then we would add it to the percent abundance of your next isotope times the mass of that next isotope, and so on and so forth. And what that would do is it would calculate an average mass for us, but the average mass would be weighted, and so therefore would be closer to the isotope that has the greater abundance. And this is a second way to calculate an average. And this average is how atomic masses on the periodic table are calculated. So we've already seen that there's 2 different ways to calculate an average. Well, there's even more ways to calculate an average. And as you go through science and you figure out like which ones of these are useful in which circumstances, you will learn about all these other different types of averages. So a third type of average is called a root mean squared average. Now, we're not going to go into like the concepts or the math behind root mean squared average, but you should know that it's a third way to calculate an average. It is an average. And this is the type of average that we use to calculate speed of molecules. And so the first formula where we find the root mean squared average speed show up is in our kinetic energy formula. So remember that funky little E is the average kinetic energy of a molecule within a body of gas. It's equal to 1/2 m, which is the mass, and then the average speed squared. So notice it's average kinetic energy and it's average speed. Okay. Now, if you have taken physics, this formula looks really familiar to you because in physics, you talk about how you have potential energy and you have kinetic energy. And when you add those 2 up, you get a total energy for the system. And potential energy is mass times acceleration due to gravity times height. So potential energy in physics is often due to the object's position, how high it is. Whereas kinetic energy is 1/2 mv squared. So kinetic energy, or the energy of motion, is tied directly to an object's mass and an object's speed. And then we have this third formula here, where if you add up all the potential energy of a system and all the kinetic energy of the system, you get the total energy of the system. So the formula for kinetic energy, compare that to this formula right here. The average kinetic energy is equal to 1/2 m average speed. And so it would make sense if we average the speed of all the molecules, we get an average of all the kinetic energy. And remember, kinetic energy is proportional to temperature. So when we measure temperature, what we're measuring is actually the average kinetic energy for our body of gas in the room, for our body of gas in the drying oven, for our body of molecules in the beaker, right? So when we're measuring temperature, we're actually it's a direct and proportional measurement of kinetic energy. And this kinetic energy is tied to the speed. Okay, so just a reminder, when you're looking at this graph of the energy distribution throughout molecules in a graph, you should be able to describe two things about this graph. It might be a good time to pause this video and see if you can recall that from the last video. So those two things that you should be able to describe by looking at this graph are that the average kinetic energy, the average energy of a warmer sample is going to be at a higher energy than the average energy contained in a cooler sample, which means that the average speed of molecules in a warmer sample is going to be at a higher speed. The average speed of molecules in a cooler sample is going to be at a lower speed. The other conclusion that you should be able to draw by looking at this graph is that molecules in a warmer sample have a larger distribution. So notice there are more molecules for a warmer sample at a higher energy, which makes sense, but there's also more molecules in a warmer sample at a lower temperature too, when you compare the proportion of this to your average, right? In a cooler sample, more of those molecules actually exist at the average. Notice that there's more molecules at the average temperature of a cooler system. There are less molecules at the average of a warmer sample, so that those warmer sample molecules actually get distributed more evenly throughout the energy scale. The cooler sample molecules tend to be more in line with each other. So there's those two conclusions you should be able to read off of this graph. Okay, so we've talked about how root mean squared speed is really an average speed of all the molecules in a sample. And root mean squared speed is related to the average speed is related and used to calculate the average kinetic energy. Now we're going to come back to these two things, average speed and average kinetic energy, when we talk about a couple more concepts like effusion and diffusion of gases. So put these two terms in your back pocket. We're going to come back to them after we finish talking about the kinetic molecular theory. So let's finish doing that. All right, so using the kinetic molecular theory, we should be able to explain a couple things. We're going to keep it consistent here, and we're going to explain the effect on pressure. So how does pressure change when volume is increased? How does pressure change when temperature is increased? Now would be a good time to pause the video and see if you can kind of bullet point this out. Like bullet point 1 would be volume increases, and then bullet point 2 is what do the molecules do because you increase volume, and how does that lead you to how the pressure changes? Pause the video here, see if you can bullet point that out, and then we'll come back together. Okay, so what you should be envisioning is kind of like what is happening to the gas at a molecular level. So if we take a gas inside a container and we expand that container, but keep the amount of gas the same, what does the kinetic molecular theory say about how that would affect pressure? So when this occurs, what's happening is each of these molecules, before it collides with something, remember pressure is force, how many times the gas molecules hit the container and how forcefully they hit the container over a specific area. Right? And the area is going to be the sides of my container. Okay, so really what we want to describe here is how the collisions are changing between my smaller box and my larger box. Okay, so in my larger box, the molecules are going to have to travel farther before they collide with a wall, or they're going to have to travel farther before they collide with another molecule. So the length between collisions is going to increase. The time between collisions is going to increase. So what we're going to see is less collisions per unit time, which means pressure is going to decrease. And you can see this here. Okay, temperature is constant, so kinetic energy and the average speed are also going to be constant. So that's not a factor that's going to affect pressure. Longer distance traveled between collisions, therefore fewer collisions with the walls per unit time, which is what we saw in that small versus big box. Therefore, pressure decreases. So that would be justifying the change in pressure when volume increases by using the kinetic molecular theory. See if you can do the same thing on the second prompt there, and go. Okay, so again, we're going to increase the temperature. So in this case, we're going to keep the container size the same, but we're going to increase temperature. So low temperature, high temperature. These are our two systems. So in the high temperature system, my molecules are going to have greater kinetic energy, therefore greater average speed. So they're going to hit the walls and each other more often and with more force since they're moving faster. So higher number of collisions, higher force of collisions. Therefore, what's going to happen to pressure? Increased pressure. Okay, now I drew pictures. I'm using like abbreviations and arrows. If this was a free response question, drawing a picture would be a really great thing. But you don't want to use arrows or abbreviations unless you have a key for them somewhere, and it's probably going to take you longer to make a key than it is just to write the words out in a full sentence. Let's take a look at this in bullet points. So volume is constant, kinetic energy and average speed will increase, more collisions with walls per unit time, harder collisions with walls per unit time, therefore pressure increases. So force over our unit area will increase, so pressure will increase. Okay, there you go. So that's kind of what, if they ever ask you to justify something using the kinetic molecular theory, really what they're asking you to do is kind of reference these 5 postulates. You don't have to reference all of them, but what they're looking for you to do is to describe it on a molecular level. They don't want the macroscopic view, okay? Volume increases, pressure decreases. That would be the macroscopic view. That's what I view in our lab, right? Usually that's what they give to you. They tell me why increasing the volume will lead to a decrease of pressure. So if you just restate the question, that's not worth any points. You don't get points by restating what they already give to you. What you want to do is explain what's happening on the molecular level that we can't see, we have to think abstractly about, which is why drawing pictures helps, and that's where the points are going to lie. Okay. Actually, I want to go through this one together in class, and because this is kind of a repeat of what we just did, and I want to give you a chance to justify this out. Same with this one. Okay, so now we get to effusion and diffusion. So they're words that are very close together. Let's kind of define these two. So diffusion, you probably have heard of, and it's when two gases mix until they're evenly distributed. So you can think like if I spray myself with perfume and you're standing at the back of the class, the perfume molecules are going to diffuse through the air of our classroom until the air in our classroom is a homogeneous mixture again. And what that might mean is by the time the perfume molecules get to you at the back of the class, you might not even smell it because they have been diluted by the other air molecules in here and kind of spread out. You know, sometimes that's a really good thing. Sometimes we don't like the smell and we're excited for the air molecules to diffuse out and mix into a homogeneous mixture where we can't detect that smell. If you've ever been around someone who microwaves like a boiled egg or a fish, you'll know what I mean. Don't get me wrong. I like boiled eggs. I really like fish. I don't want to smell your microwaved boiled eggs or fish. Sometimes it's a good thing in terms of perfume. Well, unless that perfume is the cologne of a middle school boy, which means it's probably Axe, which means it's probably not something the rest of the world needs to smell all the time. Okay, I digress. Let's keep moving on. So that's diffusion. Effusion is a similar effect, only it happens through a tiny hole. So you can think of, okay, if you fill up a normal balloon with helium inside here is actually smaller than the pores of the balloon. The balloon looks like it is a solid thing, but really there are tiny little pores in between the latex of the balloon, and the helium is smaller than those pores, and so the helium can actually escape out. And so what happens is you wake up in the morning and your super fun birthday balloon that was floating on the ceiling when you went to bed is now small and shriveled and laying on the floor. That's effusion. The helium has escaped through a tiny hole. This doesn't happen in mylar balloons, I think is what they're called, because mylar balloons, their pores are smaller than the size of a helium molecule, and so helium can't escape. Those things last forever, and they will float on your ceiling until your next birthday, unless you pop them and play with the helium. Okay, so when we're looking at effusion and diffusion, this is actually a super complicated phenomenon because not only do gases just escape nicely or travel through air nicely, but they also collide with everything in their path. There's a statistic that if a molecule of air had a straight path, didn't run into any other air molecules, didn't run into any other objects, it would be able to get from like here to Texas in a matter of seconds. Gas molecules are moving extremely fast, but gas molecules don't actually move from here to Texas unless the entire body of air moves because they just run into too many things. So it's a fairly complex process, but we can generalize some relationships out of here. Okay, so for example, here are some generalized relationships. So we know that any gas has a specific kinetic energy at a specific temperature. Light and heavy molecules, think like helium versus xenon, for example, they're going to have the same average kinetic energy. Their mass doesn't matter. Their kinetic energy is going to be the same. However, they don't have the same mass. And remember, mass is part of the equation here. And so light molecules are actually going to move faster than heavy molecules because of the mass difference. It's not a difference in kinetic energy, it's a difference in mass. And so this comes back to this formula. Okay, if average kinetic energy is the same, but mass is larger, then speed must be smaller. Okay, so mass and speed are indirectly proportional to one another. Here's a second formula that involves average speed, the root mean squared speed. It's the square root of 3RT over m, and this m here again is molar mass. So the speed is indirectly proportional to molar mass. As molar mass goes up, speed goes down. Notice it's directly proportional to temperature, indirectly proportional on a square of molar mass. And that's what this graph is talking us through. If you look at these different types of gases, here's hydrogen, here's helium. Hydrogen's going to be the lightest. Okay, and then we kind of go up in mass here. Oxygen is going to be the heaviest, right? 32 grams per mole versus hydrogen, which is 2 grams per mole. And so what you see is the average speed for hydrogen is a lot higher than the average speed for oxygen, which is much heavier. Again, notice the distribution. That lightest molecule, its speeds are a lot more distributed than oxygen. It has molecules moving quickly. It has molecules moving slowly. Whereas oxygen, its molecules are more concentrated, more focused. That more of them have that average speed, but that average speed is also slower. Okay, so again, off this graph, you can draw conclusions about the average molecular speed and the distribution of molecules. Okay, so we have two formulas that are involving our average speed or our root mean squared here. Can you write those two equations from memory? And are they on your reference sheet? Okay, I want to go through that one. Well, I guess we don't have to. Okay, let's look at this. Root mean squared equals the square root of r, 3RT? Yeah. Over molar mass. So we want root mean squared to come out in probably meters per second because it's a speed. So 3, we need to choose the correct R. Temperature is going to be in Kelvin. So that's 298 Kelvin over molar mass of N2. So that's going to be 28 grams per mole. Okay, and then don't forget your square root. So the question of the hour is, which R do you choose so that your units are going to come out to be meters per second, which is units of speed, right? If you plug in the liter atmosphere per Kelvin mole, you're going to be left with a whole bunch of crazy units. So you want to choose the R that's going to leave you with units that you want. Okay, so here's the catch in choosing the R. You have to know that 1 joule, so a joule is a unit of energy, just like a calorie is. When you eat an apple, you're eating a specific number of calories. You're eating a specific number of units of energy, right? So calories is the unit of energy that we are used to talking about. But the unit of energy in the SI system is actually the joule. Just like cups would be cups and ounces and teaspoons would be units that we are used to dealing with if you cook. But if you're going to talk about measuring volume in a chemistry lab, you're not going to use cups and ounces and teaspoons. You're going to use milliliters. Same thing with energy. We're not going to use calories. We're going to use a joule. Okay, so a joule is actually a derived unit also, and a joule is a kilogram meters squared per second squared. Okay, so because joules can be broken down into these units, that's the one you want to plug in here. Okay, so I had it pulled up here. 8.314 joules per, what was it, mole Kelvin? Mole Kelvin. Okay, now if we look at our units, Kelvin's going to reduce out, moles is going to reduce out, and then we have a joule, so a kilogram meters squared per second squared, divided by grams. So we have kilograms per gram here. We can convert this into kilograms so that these two reduce out. Then what we're left with is meters squared per second squared, and then you take the square root of that and you're left with meters per second. So the units in this problem get a little bit tricky. Again, worth working through just a couple times until you feel comfortable with this. However, I have good news for you, and the good news is usually they don't ask you to plug and chug into these formulas on a test. What they ask you for is the relationship. So that's what you have to know. You have to know speed is directly proportional to temperature, speed is indirectly proportional to molar mass, and it's a squared relationship. It's not a linear relationship. It's a squared relationship because of that square root in there. You can think of it this way, that the speed is proportional to the square, indirectly proportional to the square of molar mass. Or you can look at it this way, the squared speed is proportional to the inverse of molar mass. So whichever way makes more sense in your brain is the way you should remember this. This might be a good concept to kind of draw some pictures out and wrap your brain around those relationships. Drawing pictures of molecules usually helps. All right. When we're talking about effusion, so the escape of a gas through a hole, again, super complicated relationship that can be reduced down to this equation here. So R is going to be the rate of escape of one molecule. And notice there's the square, and then the molar mass of that one molecule is in the inverse. So again, we see this relationship of rate of escape indirectly proportionate to the square of molar mass, or the square root of molar mass. Okay, and then we can compare it to a second gas. The rate of gas 2, again, indirectly proportional to the molar mass, the square root of the molar mass of gas 2. So we see a very similar relationship here between rate of escape and molar mass than we did between speed and molar mass. And it can lead you, again, it's the relationship that matters more than the ability to plug and chug that matters. So a relationship question would be here. Which one would deflate more quickly, a helium or air-filled balloon? If you want to pause and think about it, now would be a good time to do that. And what you should come to is that the helium one's going to deflate more quickly because its molar mass is smaller, and therefore its rate of escape is going to be larger. So diffusion doesn't come with an equation because it's such a complicated process. You know, with all of the collisions that happen and the new angles that would form and the transfer of energy, the elastic transfer of energy that happens when molecules combine. Basically, again, it comes down to the relationship. Diffusion is going to be faster for light molecules than heavy molecules, very consistent with what we've had to see before. You might hear this term, the mean free path, and that is, again, a mean is kind of like an average, but free path is talking about how far that molecule can travel before it runs into something else. I'll give you a hint, it's not super far. This would be a good question that comes out of that term. Would you expect the mean free path to be longer for a molecule at low pressure or high pressure? Again, this would be a good time to pause and think about that. And again, thinking about the kinetic molecular theory assumptions would help you with this one, because at higher pressure, remember, you're going to have the molecules closer together. And so the mean free path is going to be shorter. At lower pressure, your molecules are going to be able to expand and spread out from each other. So the mean free path is going to be longer. Oh, not notes. Okay. Last concept here is talking about real gases. So we have been talking about the ideal gas law for a long time. So ideal, if it's an ideal gas law, it's behaving consistent with those 5 assumptions in the kinetic molecular theory. However, like all of our models that we have seen in chemistry, our model is going to break down at the extreme. And so we want to talk about what these extremes are and why our molecules break down there. So there's a couple of problems with the kinetic molecular theory. First of all, the KMT assumes that the gas molecules, the protons, neutrons, and electrons of a molecule, occupy no space, which they don't. They are matter, takes up space, has mass. They do take up space. When gas molecules are far enough apart, the volume the molecules takes up compared to the space is negligible. When that space gets smaller, however, the space the molecule takes up becomes more significant. It becomes a bigger proportion when compared to that space, and it tends to become more significant. So anytime molecules get forced closer together and that space is diminished, all of a sudden the volume of the molecule itself is going to make an impact. So that would be under high pressure, or that would be under low temperature when things start to move more slowly and then they don't bounce so far off of each other. Under those conditions, so high pressure, low temperature, the kinetic molecular theory starts to break down. Gases do not act as ideally, and we have to talk about the real gas behavior. A second problem is gas molecules have no attraction to one another. Again, if you get molecules close enough together, that attractive or repulsive forces starts to act on the gases. So again, higher pressure forcing them together, lower temperature, the molecules moving more slowly and coming closer together. That attraction is going to start being significant. And then we have to take it into account, and our ideal gas laws don't work at predicting outcomes as well. Okay, so again, it's going to happen at the extremes. So under high pressure, the deviation is large, so they're not going to act as ideal. The ideal gas law is not going to work as well to predict behavior. Temperature, at low temperature, again, the behavior is less ideal. And it's all about reducing the space between molecules and allowing the molecules close enough to have an impact on one another. This thing needs to stop. Okay, so there is an equation. It's a modified version of the ideal gas law. So it's PV equals nRT modified, and it's called the van der Waals equation. It looks like this. You can still see we have PV and RT in here. They're still proportional to each other in the same way, but we have a couple new factors that take into account some of these considerations that we have to make when the normal model starts to break down. Now, you don't have to memorize this formula. You don't have to be able to plug things in and solve an answer out of this formula. If you ever needed these factors of A and B, you would be able to go look them up for a specific gas. You just have to know that they are going to account for attraction and the actual volume occupied by the molecules of the gas. These are the two things that A and B are going to account for. And again, if you ever needed them, if you go get your doctorate in gaseous chemistry or atmospheric chemistry or something like that, you can always look up A and B in a reference book. And then here's an example. Now, this example, it actually has you plug in A and B. It gives you A and B and plug in. This example is actually beyond the scope of our class. They're never going to ask you to do this. What they're going to ask you to do is explain why you might need to do this or what A and B are compensating for. And then this one kind of pulls it all together so we can try this one together in class. So congratulations, you made it through chapter 5. Good job, you guys. I'll see you in class for some practice.